All right, good morning. We are on lesson 9.2, problem 2, page 538. All right. The doctor will see you now. The Center for Disease Control collected data on the percent of children aged 12 to 19 that were considered obese between the years of 1971 and 2007. The data is given at a table. So, what do we, just with our eyeballs, see any sort of pattern?
Yep. Oh, yeah. As the years increase, the percent of obese children increase.
Okay. 18% is close to 20. 20 is like 1/5. 1 in 5. Identify the independent and dependent quantities in this problem situation. Just from the data they give us. What's the independent quantity and what's the dependent quantity?
The independent is the time and the dependent is the percent of obese children.
Good job. Independent is time measured in years. Dependent is percent obese children. Construct a scatter plot of the data using your graphing calculator. Sketch the scatter plot, label the axes. All right, so let's go back to looking at that table of data. You're going to need your calculator. One thing that we've found useful in years is to go ahead and convert those years into like a beginning number. Let's see, will that be useful this time? Yep, I think so. So let's call this time 0. This is 5 years later. To figure out how many years later, I'm going to take 88 minus 71. 88 minus 71. Clear. 88 minus 71. 71's my starting point. I'm comparing all the other years to 71. I'm going to go 99 minus 71, 28. And now 2001, I got to subtract this to figure out how far apart they are. 2001 minus, we can do that in our head, yes. If I turn my brain on. If that was 30, this is 32. If this is 32,
32.
and, 34 and 36. Okay? So now I'm going to go into list, stat, edit, to list. I need to clear out yesterday's problem. Clear, enter. Second list. Clear, enter. Okay. Now I'm going to put these numbers in list 1, and they're going to serve as my x value. I'm going to put the percents in list 2, and they're going to serve as my y value on a scatter plot. So go ahead and enter that into your calculator as well. Okay, double check your lists are the same length, and then take a look at something like 28 matching up with 14.8. Yeah, it looks like things are even. All right, kind of scan your list and see, Do the X's and Y's that are supposed to be together, are they lined up together? Good? So far, so good. Okay, we're going to do a scatter plot. One of the first things that we need to do is make sure scatter plot's turned on. It should be, but it doesn't hurt to double check. So we push second stat plot, then enter. The one that should be, it should have on blinking, and the stat plot is the first one in type. So we're good there. The second thing we're going to do is adjust our window. Our X values are in list 1. What's the smallest and biggest number there?
0 and 36. Maybe we should go like 38 or 40.
Why don't we go 0 to 40, and I bet we can go by ones. That's not very big spread. Okay, how about percents? What's the smallest and largest?
6.4.
5.0.
Oh, yeah.
So why don't we go 0 to 20 and go by ones. All right, so we looked at X min and max, Y min and max. That's going to give us something with the right proportions. Once we have stat plot on, stuff added to our lists, and a good window, we push graph. And now we're going to sketch that graph over in number 2A. Okay, so let's take a look at 2A. I gave myself an X and a Y axis. I'm going to remember that my X was the year, and the Y was percent obese children. Okay, and then I'm going to copy the pattern. Are you with me there? Okay, don't forget it said label axes. If you didn't already do that, label your axes. Do you think a linear regression equation would describe this? Would best describe this situation? Does it look like we have a linear pattern? It's a kind of, because we kind of see it kind of curving at the top. It's hard to tell, but it's somewhat linear. What do you think?
Yeah.
Okay, so, yes. Yes, let's give it a try. We see a bit of a linear pattern. They're definitely not scattered all over the place. Okay, they appear to be lining up in a line, but we do notice something happening at the end there. Use the graphing calculator to determine whether a line of best fit is appropriate for this data. Determine and interpret the linear regression equation. Okay, so we got to go into stat and do linreg. And we're also going to do the correlation coefficient. That's that R value we were working with, right? So we already have our data. We go stat, calc, down to linreg. Whoever's music's on. Is that you, Memo? Oh, it's all right, we'll let Ruby do her thing. All right, here we go. Linreg, enter. It double checks with you as your data in list 1 and list 2. Yeah, we're good. I just push enter to get all the way down. And here's what we get. Okay, so Y. Did you put your years in where you did the little subtract, or did you do them as full on years?
Yeah.
It's the same. It's just that her numbers are longer. Or was it just like short?
Rounded. Yours got rounded.
Not rounded, but on R, we have, mine has says 2, that means 0.98, and yours is 0.98.
Okay. So you just have 2 digits. Okay. So y equals, notice the pattern is y equals ax plus b, and they tell you what a is and what b is. I'm going to call this 0.38x plus 4.7. And the correlation coefficient is the R, that's 0.98. Okay, but wait a minute. Determine and interpret. What does it mean when it says interpret?
Solve it. Understand it.
Understand it in terms of the problem situation. Okay, so this is the y-intercept. Okay, y-intercept, if I look at my graph, is percent obese children. Okay, what was my first year?
1970.
My 0 wasn't actually 0 as the start of time, but I'm going to put in parentheses 1971. Maybe that'll help us out. That once you hit the y-intercept, you're really talking about what's happening in 1971. So in 1971, we started with 4.7% obese children. Then this is the slope. It's 0.38. Let's call that a third. Okay? Third. That's close to a third. A third is like 0.3333, lots of threes. Then the percent increases because the slope is positive and the scatter plot's going up by 1/3 of a percent per year. What a slope means in a linear regression equation is rise over run. What that means is, if I had a line here, how much up and how much over do we go each time we move? So for every year that we move across on the line, we're going up about 1/3%. That's what this 0.38 tells us, rise over run. And the run, or the x, are years. Okay? Being able to write something that relates back to the situation is, again, the divider often between the A's and the B's in the test. A lot of you are getting good at the calculator, getting good at the math, but what the move towards Common Core Standard said is good at calculator, good at math doesn't mean you know how to use it. And it's hard. It's not easy. That's why we're trying to practice it. So make sure you're noticing that piece in directions and then trying to, as best as you can, relate it to cookie sales, cars, speed, height of balloons, whatever that problem has to do. Try and think about the situation and what does this math tell you. Okay. For the B, we didn't have to interpret. It's 0.98, but now we talk about here. This is the R. Would a line of best fit be appropriate? Explain your reasoning. We're going to use this R value to answer that. Does this R show a strong or a weak association?
Strong.
Strong, because what are the two extremes in these R values? Positive
Negative.
and negative what?
Association.
1. Positive and negative 1 are the strongest associations. What's the weak association?
0.
0. Okay, so this number is very close to 1. the R is very close to 1, so this is a strong association. When you have a strong association, that means a line is a good fit. I mean, we were wondering because we could kind of with our eyeballs see a curve, and maybe a line isn't the right pattern to describe the data. But when you have an R value of 0.98, we can say, yeah, this is linear. Let's use a line to describe what's going on. Flip the page. Probably a good time to